Hi everyone, hopefully everything is working. Just checking with the stream. Yes. Okay, so today I would like you to talk about LiteDIP, which is bridging the gap between, or hopefully bridging the gap between open hardware and open OSs, and with a nice repetition on the word between in the talk. My name is Martin Perez. I'm currently working with Intel, but this is a very personal project, so this is really just a hobby. So the agenda for the talk is gonna be, so why start a new project, then why is it about FPGAs and why people should care about this now, and then basically what is missing currently in the FPGA world or the ecosystem, and then finally what is LiteDIP. So sorry for the lack of animations. I just finished the slides and didn't have time to enable animation. Or some of them have it, some don't. Sorry about this. So why start a new project? Well, I mean, I needed a new hobby, so I've been working for Nouveau for years, and in the past, well, about 4 years, I've been working for Intel Graphics CI. Well, Nouveau was a very good way to learn about reverse engineering, and I mean, NVIDIA has pretty elegant hardware designs, so that was quite nice. And it teaches about hardware and how to think from a hardware engineer point of view. Then Intel Graphics CI taught me quite a bit about quality and how hardware designs impact quality. What might be like, oh yeah, that's simple and you know that can work very nicely, can turn out being an integration disaster later on. This is nothing that is Intel specific, but this is something that I've seen there because I've been working at Intel. And then also working with the Intel display driver team, this motivated me to make my own because, you know, how hard could it be? And then, of course, I'm sure there's going to be plenty of issues, but, you know, I just want to learn. And I mean, funnily, Ben Widowski also called for an open GPU last year. At first, I was like, I mean, why now? We've been talking about GPUs using FPGAs forever. And where are they now? So why now would be a good idea? Well, let's go through that. So, I mean, strictly speaking, like, what is left to be done in the open source world? Drivers are nowadays pretty much production ready, and I'm talking about GPU drivers, which were probably the worst for quite a while. So this is really good that we are now to this level. Of course, there's a lot to be done. There's a lot of CI to be done to maintain this production readiness, and there's plenty of things on this field. But other than this, well, are we done? Are we gonna finish there? No, of course not. We need to go further and design our own hardware that we can modify it in the same way that we modify source code. So, is there anything that has changed in the FPGA world that would make it more interesting now? Well, of course, the hardware capabilities keep getting better, and well, I mean, as a tongue-in-cheek, I put that we can implement 10 years old hardware nowadays in FPGAs, and sounds about right. Probably can do much better too, but generally, like, the level of expectations that we could have is this. And so let's say that 1080p frame buffers is definitely achievable, and even more. And also, I mean, the most interesting thing for me is that the languages and the workflows have evolved. We can now have open source flows all the way through, and that means you take open source code, you generate the bit stream, which is what is being stored in the FPGA to configure it. And basically all of this is done using open source software. I just thought that I didn't say what an FPGA was. I'm sorry about this. This is reprogrammable hardware. If you want more information, I strongly suggest you look at Ben Widowski's presentation from last year. And these FPGAs used to be configured using Verilog or using System-C or languages like this, which are not the best. I mean, they are pretty hostile. It's not as bad as writing assembly, but it's a bit like writing C. You're shooting yourself in the foot quite easily. And this is even more so that you have multiple clock domains everywhere and synchronization. And after some time, you know, people just agree that, hey, this way of working is the best. And then if the language doesn't evolve to make this let's say the proper way being easy to do, then you keep shooting yourself in the foot forever and ever, like memory issues on C. So that is better. And then there's also a lot of powerful IPs that are now available. And of course, the powerful IPs or the hardware blocks are also coming from the fact that the FPGAs themselves are more powerful. Sorry. So how does it look on FPGA? Well, if you want to see a very simple one, this one is the Icebreaker, which is basically like an Arduino but with FPGA inside, so you can do it's the same type of devices that you would be able to make, except this would be much faster. And if you want to make your own display controller, then that would be already sufficient. For CRTC, for VGA or things like this. But of course, if you want to go with HDMI, that doesn't really work. But then you have also this type of beast, which is PCI Express based with I think it was 8 gigs of HBM2 memory with half a terabit per second bandwidth. Well, a pretty big fan, one must say, and transceivers that can go like to hundreds of gigabit per second. So pretty good stuff. And yeah, sure, you can make some wonderful 8K outputs with that. You don't have to spend the $3,000 that this is on the market, like used on eBay, but that's definitely a possibility. So yeah, the FPGAs are now ranging from 1,000 of LUTs, which is the basic unit for logic, to over 1 million. But on top of this, there's fixed functions that are integrated in these FPGAs. So of course you can just have an ARM CPU there. That's pretty practical. But you can also have, so as I was saying, these the link speeds, the hundreds of gigabit per second. It's basically because there is this fixed function block that takes a parallel bus as an input and then outputs it as a single serial connection. So you can imagine that using this with a memory controller is pretty darn efficient. That works very well. Same for HDMI or DP, and you can actually get to 8K using them. So it's pretty good stuff. Then you can have DSPs, which are basically MAD blocks, and you can have multiple tera operations per second. So in integer, like 8-bit integer, of course, but still, you know, it's pretty decent stuff. There's memory controllers, DDR or HBM, although this one is not really a fixed function. PCI Express controller, so you don't have to do it yourself, and you know, things like this. So now that we spoke about the FPGA, then what about this workflow to generate to take the language, the hardware description language, and convert it into well, the bit stream, which is the configuration for the hardware. We have the project called Symbiflow, which is aiming to be the GCC of FPGAs or the Mesa of FPGAs. And so here is the matrix that is of what is supported, and you can see that there's basically 3 FPGAs that are fully supported. There's the ICE40, the ECP5 from Lattice, all of this done through reverse engineering. QuickLogic, which is not the biggest manufacturer of FPGA, decided to just provide all the documentation that is needed for implementing Symbiflow, and I think they've been contributing themselves, so pretty good. We've got an open, a vendor-supported open source, not driver, but like not compiler either, but call it whatever you want. And then Xilinx is the leader on the market. It's a bit like NVIDIA for graphics, and the project X-Ray is doing reverse engineering, and things are working pretty well. I mean, they're working so well that I'm getting ahead of myself. I'm sorry. So that's Symbiflow, which is basically just compiling, but then to generate the code that is used as an input, which is usually Verilog, you can write some higher level code, and one of them, one hardware description language, is called Migen, and this is Python based. It's very, very nice way of writing blocks, because Python is really well suited to create templates of IP blocks and then configuration of these IP blocks. So it's pretty practical. I'm going to type check. Okay. With this language, Migen, there's been a project called LiteX that is basically a library of hardware blocks which can be mixed and matched, and these blocks are connected or exposed to anything through a bus, and the bus is wishbone bus. So basically what it allows you to do is you create these blocks, you put them on the bus. They're going to be at separate addresses, and then you can expose these bus through PCI Express, through Ethernet, through UART, whatever works for you. And if you are wondering what can be done, I'm not sure if it's really readable, so I'm going to read it for you. So there's a DRAM controller with over 20 gigabit per second bandwidth, so pretty decent. Yeah, what they're showing is DDR3 connected. There's Light PCI Express block, which supports PCI Express Gen 2 with 4 lanes. You've got DMA engines to enable, well, DMA. And really, if you want to instantiate one DMA controller, it's 2 lines of code. That's it. So it's very nice. Then, as I was talking about, there was the wishbone bus and then wishbone bridge. So here the bridge is connecting PCI Express to wishbone, and it exposes the bus through bar 0. Then you've got an Ethernet controller. You've got a UART controller, SD card, serial. XADC is Xilinx analog to digital converter, which also exposes some values like the temperature or the voltage of the different buses that are there. You can access flash memory using SPI block that is there. You have Light Scope, which is a block that enables, well, in a sense, it's a bit like you would have for performance counters, but this time it's more for debugging, so it's even lower level than JTAG. And you've got HDMI input and output that supports full HD at 60 Hz, and that can definitely be improved to support higher resolutions, but right now it's a pretty old version of HDMI that is implemented. But again, like most users would already be fine with this. So LiteX and Symbiflow put together, well, you can create a device using one line of code that has well, the DRAM for your device. So let's say like half a gig. And then you have a quad-core RISC-V CPU that is running Linux at 100 megahertz. So this is something that doesn't exist in hardware, but then you can already play with this using an FPGA. It's pretty cool. Then if you want to know what boards exist, so on this front of the ecosystem, there's more and more boards that pop up, mostly thanks to Symbiflow making dealing with FPGAs much better or much easier. So this one is not out yet. It's the ULX3S. As you can see, it has pretty much everything you might want for a handheld console. HDMI output, a jack, 2 USB outputs, or 2 USBs, micro SD, there's Wi-Fi, there's Bluetooth, there's buttons directly, there's SDRAM, and as a matter of fact, people have been already using this to emulate, I think it was a 286 Intel platform, and then running DOS on this, and so you could run DOS games on this, and that's properly emulated. And there are already emulators like this for a lot of consoles, so you can buy this device, and then if you want to play, I don't know, old games that run exactly at the same clock, no emulation, well, it is in a sense, it's hardware emulation, but basically like it's perfect. You can't beat that. And yeah, and then you can switch to Game Boy, you can switch to newer stuff. Of course, things have to be written first, but there are already some existing things that prove that it can be done. Then there is the NETV2, which is not exactly new, but it's a very cool device. So it's Xilinx based as opposed to the other one, which was Lattice. So this one is not completely fully supported yet by Symbiflow. So this is a device that I have, and this is what I'm trying to make the project run on. And this one has PCI Express and there's basically 2 HDMI inputs and 2 HDMI outputs, and this is what I'm trying to use for making my own play controller. I'm going to talk to you about this. So what's missing about this entire ecosystem? Well, one of them is upstream Linux drivers. So you can make an SoC in 10 minutes using LiteX, but then you'll have to write your own driver for it, which is not exactly cool. And there is work going on the LiteX work, which is a LiteX world that is basically using the device tree to expose the addresses of the different blocks. But I would working on making this discovery straight on the bus, which means that no matter how you access the bus, so let's say you run a soft CPU or you run on PCI Express or USB, you would have the same driver for everything, and this driver would instantiate other drivers with the right parameter. So in any case, it's what I'm working on. So the current state of it is that I'm iterating on more effective ways of getting this discoverability done without using too many gates on the FPGA, and also having the cleanest driver possible. And so far it's pretty good. I mean, the discoverability is like 200 lines of codes or something like this. It's really not bad. I've been really caring about quality from the beginning. So for testing, I do hardware unit tests for all the blocks that I have. Not complete yet, but that's what I'm doing. For driver, I have unit tests with CMOCA, and in the end, I'm going to do integration testing with QEMU and running my design using Verilator, which is a simulator of hardware, and connect this device, this PCI Express device, to QEMU to expose it to Linux, and then run basically the entire stack in simulation. So that needs to be done. The others have done, but not that. So the current blocks that I have, well, the first one is boring. It's just text saying, hey, the author is this person, and then the name of the device is that. Okay. Then there is a way to expose sensors. So any kind of sensor, which is interesting because, the driver doesn't know what device it's gonna be running on. So the device itself has to tell everything about what it exposes and how to interpret the value. So it tells you the unit, the calibration function, and it allows you to read a 16-bit value and then say, well, that means it's 16 degrees or it's 80, and then it also exposes the limits for these values. So in HW1, you can see if the value that you see is actually good or not, and this is done in without having any hard-coded values. That's pretty cool. And of course, because I was working so much on for Nouveau on power management, I implemented my own fan controller with a tachometer for the fan speed. That was a cool project, and yeah, so it's pretty cool. It's not merged yet in master, so if you want to see it, you can go to the fan work in progress branch. Okay, so when can we expect a full GPU? Well, let's be realistic. That's really not the first thing we need to do. First thing would be to expose the current LiteX blocks, and then my objective, as I was saying before, is to create a USB/PCI Express display controller and have the same code generate bitstream for 2 different boards and FPGA manufacturers. So that would be lovely. The ETA was, well, let's do this by XDC, which was not a crazy target, but then life came in the way. Of course, the pandemic was a way to get more time, but then with my girlfriend decided to buy a house, get a dog, and I think you get the feel of how things go. And I've been interacting more with the LiteX community, and that led to a lot of redesigns of the core, and so that slowed me down. And of course, XDC, the organization of XDC has been taking some time. Okay, so I'm already over time, but maybe there is one question or two that I could select. So Radek was asking about Intel and Altera. Right now, there's basically no reverse engineering efforts on this front, so that's why it's not mentioned. And Adrian is talking about the DE10 Nano, but I don't know what it is. Okay, well, thanks a lot for your attention, and I'm going to switch back to Arek, and Luke is going to be presenting in 6 minutes the LibreSoC project, which I guess is anyway much closer to the GPU, open GPU than the LiteDIP is right now.